In this lesson, we're going to take a look at inverse trig functions. So that word inverse should be familiar to us. We've definitely studied it before in pre-calculus 1. So let's just kind of review this idea of inverses for a moment, and maybe let's do it with trying to solve an exponential equation. So let's say I have e to the 2x is equal to, let's say, 4. And so I want to solve for x, but right now x is in the argument of this exponential function. And so what we'd really like is a way to kind of undo the exponential. And so if you recall from pre-calculus 1, the remedy for this is to go ahead and take the natural log of both sides. And in doing so, what happens is the natural log kind of undoes the exponential, and you're left only with 2x on the left side. And then the only thing standing in the way of getting x by itself is to divide by 2. And so you end up figuring out that x is equal to the natural log of 4 divided by 2. Okay, now that's all just to do something familiar to kind of remind us of this idea of the inverse. And so what the important part of all that is that, at least the important part for what we're doing in this lesson, is to understand that the reason this all worked was because of the idea that the function f of x equals e to the x, so the exponential function, and the natural logarithm function are inverses of one another. Okay, so they undo one another. So these are inverse functions. So we've been studying trigonometric functions, and in particular today we're going to look at sine, cosine, and tangent. So the idea is, okay, can I find an inverse function of the sine function, or the cosine function, or the tangent function? All right, so just a couple of things to remind us of. In order for a function to have an inverse, it must be a one-to-one function. And so remember what that means is that every single y value only has one x value associated with it. Okay, so just as an example here, if I have just, let's say, a line, let's say y equals 2x, this is one-to-one. And the reason it's one-to-one is because if I look at any particular y value, there's only one x value that goes with it. Okay, but contrast that with, say, a function like, y equals x squared. Y equals x squared, this is not one-to-one. And the reason it's not one-to-one is because I can find a whole bunch of y values, infinitely many in fact, that are going to have two x values associated with the same exact y value. In other words, it fails the horizontal line test. Okay? And when a function is not one-to-one, that means it does not have an inverse. Okay? So that's one fact we just have to remember here, is if we want our sine function, our cosine function, etc., to be able to have an inverse, it's got to be one-to-one. So that'll be an issue we'll have to address. All right, but if you do in fact have a one-to-one function, then remember that the way we define the inverse is to say that if you take the inverse applied to y, you'll get x, where if you applied the original function to x, you would get y. So it really just undoes things. It takes you from the output back to the input again. So if I was to write our exponential and logarithm functions that we talked about on the previous slide in this way, we would say something like this. The natural log of y equals x is the same as saying e to the x is equal to y. And this kind of setup should look really familiar. This is in fact how you originally define the natural logarithm back in pre-calc 1. Okay, so supposing that we have a one-to-one function, I just wanted to show an example of what happens on the graph of a one-to-one function. Excuse me, on the graph of a one-to-one function, if we graph both it and the inverse. So here's an example. F of x equals x cubed in blue is a one-to-one function. It passes the horizontal line test. And so its inverse, the thing that undoes the cubing of x, would be the cube root. Okay, and so you can see how, for example, if I take the cube root of 8, I'm going to get 2. Why is that? Because if I take 2 cubed, I get 8. And so you can see this idea of, okay, F inverse of 8 is equal to 2. F of 2 equals 8. Right, so you see this undoing property. But if we think of these things from a graphical standpoint, understand that what we're saying is, in this case, the point 8, 2 is on F inverse, right? But then this is saying that the point, that the point 2, 8 is on F. And that's clear from the picture here. So if I look at 8, 2, here's 8, 2, and here's 2, 8. Okay, so we can see that here, but it's more general than that, right? So what we can say now is that if AB, any particular point AB is on F, then BA is on the inverse. Then BA is on the inverse, okay? And so essentially what you're doing is you're just swapping the x and y values on the graph. All right, so with all that being said, when I was talking about the fact that we need to have a one-to-one function in order for us to be able to find the inverse, you may have already been thinking about the shape of the sine function, and in your mind thinking, wait a minute, that's not one-to-one, because I know the shape of the sine function by now, and I know that it does this, and it really does this, and so I can clearly see it's failing the horizontal line test, right? It's got multiple x values associated with any particular y value, and in fact it's worse than that, since the sine function continues off forever to the right and to the left. In fact, there are infinitely many x values for any given y value. So the idea here is, while I can't find an inverse function for the sine function as we've been studying it, what we can do is restrict the sine function so we force it to be a one-to-one function. So we're going to restrict the domain of sine to only go from negative pi over 2 to pi over 2. The reason I make those choices is because at negative pi over 2 I can see that the x value is negative 1, or sorry, the y value is negative 1, and then I'm going to climb all the way up and get to the positive y value of 1 by pi over 2. So in other words, I have encompassed all the possible y's that I could get as a result of taking the sine of any particular x value within this interval of x values. So in other words, I won't miss out on any y values by doing this, but now this restricted function is one-to-one. So if that's the case, then I can define my inverse sine function in this way. It is the value that basically undoes the sine. Okay, and so if the domain of our restricted sine function is negative pi over 2 to pi over 2, and we know that with these graphs the x and y's are just switching, then that means the range of my inverse function is negative pi over 2 to pi over 2. And because we can see from this graph that the range of sine is -1 to 1, that means the domain of my inverse sine is -1 to 1. So you'll see this notation here, just y equals the sine inverse of x. Okay, so this is not a -1 exponent. Okay, this is just the way we designate the inverse sine. Another way you'll see it written is as the arc sine, and that just means the same thing. It's tradition to, to use the this idea of an arc sine to indicate the inverse sine. Okay, so that'll be another way that you'll see it written. All right. All right, so a lot of information on this page. Some of it I went over on the previous page. So the sine inverse has a domain -1 to 1 and a range -pi/2 to pi/2. So here's what it ends up looking like. Okay. Now let's understand here that just to kind of make sure that this seems to be making sense. Let's go ahead and just sketch the graph of sine over here. So pi/2, understand first of all, is about 1.57. That's the approximation for pi/2. So that would put 1 right about here. Now put -1, I suppose, right about here. Okay. And then we've restricted ourselves in the sine function to go from -pi/2 to pi/2. So if this is 1 right here, then let's 1.57 is going to be about there, and -1.57 is going to be about there. So that's pi/2, and that's -pi/2. So my purpose in this is let's just make a quick sketch of the sine between -pi/2 and pi/2. So I've got those, and I'm at 0 at x equals 0. And so notice if I graph this, okay, there would be the restriction of my sine function. And if you recall, what did we say? For every pair that I have on the original function, I should have the x and y values swapped on the inverse. So, here I've got the point pi/2, 1. But guess what this point is? This is the point 1 pi/2. Okay, so here's the graph of the sine inverse. Okay, now for the most part, when you're working with inverse trig functions, you're probably not going to think a lot about the graph. What's a lot more useful is to think about the range of angles that the inverse spits out. Okay, and so the important part to understand here is that when you take the sine of an angle, it gives you a value of the y value on the unit circle, right? That's what the sine function does. So what's important for us to understand is that the sine inverse takes a y value on the unit circle and spits out an angle. So in other words, we have to understand that what's being spit out of the sine inverse. So the sine inverse outputs angles. And that'll really help you kind of keep your bearings when you're thinking about this. It outputs angles. And this picture down here describes which angles it's going to output. You can see it from the graph, right? It's going to give, from -pi/2 to pi/2 are the things that this function outputs. But I think this picture sticks in your mind a little bit better. Okay, so remember it goes from -pi/2 to pi/2. That's the angles it's always going to spit out. So let's put this into practice a little bit. All right, so example 1 here asks us for the sine inverse of the square root of 3/2. Especially when you're starting these, here's the way to start this. First of all, understand that the answer that it wants you to give is an angle. Okay? So it wants to know what angle has a y value on the unit circle of square root of 3 over 2. And if it makes you feel more comfortable, go ahead and feel free to re-express this. This means, by our definition of the inverse, this means that the sine of theta of this angle that I'm looking for equals the square root of 3 over 2. Okay, so let's look. On this right half of the unit circle, when is the sine square root of 3 over 2? Well, the sine is the y value, so that would happen here, right? The square root of 3 over 2 is the longer side of the triangle that gets formed. Okay, so this is the point 1/2 square root of 3 over 2, and we know that that happens at the angle pi over 3. So that's my answer right there. Theta, if this is true, must equal pi over 3. So therefore, sine inverse of the square root of 3 over 2 equals pi over 3. Right? That's my answer. All right, let's do another one here. The arc sine of negative 1/2. So again, arc sine of negative 1/2 equals an angle. So then we're going to ask, what angle is it that when you take its sine, you get negative 1/2? Okay, so over here I want the sine, or the y value on the unit circle, to be negative 1/2. So that puts me, right about here. And we know that that happens at square root of 3 over 2, negative 1/2. But let's see, what angle is that? Well, that's definitely, we recognize as the angle 11, excuse me, not 11, negative pi over 6. Okay. I almost caught myself doing that there. Yes, that is 11 pi over 6 when you go all the way around, but remember, we're restricting ourselves to go from negative pi over 2 to pi over 2. So that would be negative pi over 6 there. So theta is negative pi over 6. So there's our answer. So again, when you are taking the inverse sine or the arc sine, you are going to give an angle as an answer. All right, last one here, the sine inverse of 2. Again, what does that mean? That has to equal theta. Okay. Whoops. So that's going to equal this angle theta. So what does that mean? That means that the sine of theta is equal to 2. Okay. Now that should make us pause for a moment. The sine of theta equals 2. Is that even possible? Let's remember that sine is always between negative 1 and 1, right? So you could never get on this unit circle here, you could never get a y value that's more than 1. And think about the graph of sine. It never gets below negative 1. It never gets above 1 if it doesn't have some sort of a larger amplitude. So this is impossible, right? Right? This is impossible. And so if we're being asked to do something impossible, what we of course say is that the sine inverse of 2 is undefined. All right, so let's take a look at the cosine now. The cosine has the same problem that sine did, in that it is not a one-to-one function. Right? So, again, you're remembering the fact that here's what cosine really looks like. Right? So that's definitely not a one-to-one function. So we need to restrict it, but this time we restrict it differently, right? If I use the same restriction as for sine, negative pi over 2 to pi over 2, I would only get these positive values included, and I want to include everything all the possible y values that cosine spits out. So instead we're going to restrict from 0 to pi, and that'll get both the positive y values and the negative y values in there. And so then what that means is when I define the inverse cosine, its range this time is 0 to pi, and its domain is -1 to 1. All right, so down in the lower right corner here, you can see the inverse cosine graph. But again, for practical purposes, you're probably going to want to pay a lot more attention to this picture here and understand that cosine inverse is always going to output angles between 0 and pi. Right? It's always spitting out an angle, and it'll always spit out angles that go between 0 and pi. So let's do a little practice here. So the arc cosine of -1, right, again, that's equal to an angle. So that means I'm looking for an angle that gives -1 when you take the cosine of it. And so you can see on the unit circle, this would be the spot right here where the cosine is equal to -1, right? Or the x value on the of the point on the unit circle is -1. And so theta must equal pi. And so there's your answer. All right, so let's look at the cosine inverse. The cosine inverse of -√2/2. We want that to spit an angle out at us, right? And the angle we want it to spit out is the one that if you take the cosine of that angle, it gives you -√2/2. All right, now there are two places, understand, on the unit circle that would give you a negative cosine value of -√2/2 cosine value, right? One would be down here, and one would be up here, right? So this one here would be at 3 pi over 4. That's going to have a terminal point of -√2/2, √2/2. Erase that. But of course, we also see it down below in the third quadrant. Excuse me, let me fix that real quick. In the third quadrant, we see it down here, and that would correspond to an angle of 5 pi over 4. Okay, and that would also have a cosine or an x value of -√2/2. But the thing is, yes, there are two places on the circle where you get that cosine value, but only one within our restriction. So we restricted ourselves to go from 0 to pi in terms of our angles, so I have to give the answer that is within that 0 to pi interval. So 3 pi over 4. All right, now finally, I'm going to jump back to sine inverse for a moment. So I want the sine inverse of -√2/2, and that's equal to some angle. So I am looking for the angle that if I took its sine would give me -√2/2. Understand that the moment I ask about the sine inverse, the picture that we have in front of us in this problem is no longer useful. I have to go back to the picture of the unit circle, but I need to go back to the one for sine inverse so that I know what angles the inverse sine spits out. And remember, it spits out angles between -pi/2 and pi/2. So this is the picture I need to go back to. So the sine, where does it equal -√2/2? Right here. So we've got an angle of -pi/4 when I'm looking at the sine inverse of negative root 2 over 2. So just wanted to emphasize here, this these pictures are really important. For cosine, it's this picture, the upper half of the unit circle. For sine, it's the right half of the unit circle. All right, finally, let's take a look at tangent here. So for tangent, we know that, really tangent continues on a lot more than what you see in this picture, right? So, it continues on like this. All right, we have infinitely many vertical asymptotes, and it just goes on and on. But clearly, this is not a one-to-one function. So tangent also needs a restriction on it so that we can take an inverse. So the natural one would be to just grab the one in the middle and recognize that this asymptote is negative pi over 2. This asymptote's at pi over 2. So my inverse tangent function will be a function that has a range equal to negative pi over 2 to pi over 2. Notice I'm using parentheses, not brackets, because they're asymptotes, so I'm not actually allowed to equal negative pi over 2 or pi over 2. And then my domain is all real numbers because I can see the range of tangent is all real numbers. All right, so notice that the picture for tangent here in terms of the unit circle is the same as the picture for sine. So it also has a restriction of negative pi over 2 to pi over 2. So when you're trying to keep track of all this, just remember that the cosine's the odd one out. It's the upper half of the unit circle. Those are the angles that it spits out. But both sine and tangent spit out the right half of the unit circle in terms of angles. All right, so let's do 2 examples with tangent. Tangent can be a little more involved, so let's take a look at the tan inverse of negative 1. So again, it's definitely still the same strategy here. The tangent inverse gives me an angle, so that means I am looking for an angle that if I take its tangent, I get negative 1. So in order to be getting negative 1, understand, I know that the sine and the cosine, or if you prefer to think of it as the y value and the x value on the unit circle, must be the same value but a different sign. They would have to be the same value to give me 1, and then they would have to be different signs so that when I divided them I got a negative. Okay, so where in this range of angles are the x and y value the same value but opposite signs? Well, that's definitely going to be down here, right? That's going to be here at square root of 2 over 2 as the x and negative square root of 2 over 2 as the y. That is going to give me negative 1. Okay, and of course this, right, this happens at theta equals negative pi over 4. So there's my answer, negative pi over 4. Is there another place on the unit circle where the sine and the cosine, or the x and the y, are the same absolute value but different signs? Sure, it happens up here. However, the reason that's not our answer is because we restricted the tangent to negative pi over 2 to pi over 2, and so tan inverse is only going to spit out values between negative pi over 2 and pi over 2. All right, so then if I take the tangent inverse of the square root of 3 is equal to theta, then I know that the tangent of theta must equal the square root of 3. And so what we should be thinking about here is, okay, where is the ratio of the y to the x going to be equal to the square root of 3? So what the game I like to play here is to take that square root of 3 and say, okay, well, what's the special value on the unit circle that has square root of 3 in it? Well, it would of course be the square root of 3 over 2, right? But I can't just divide by 2 up top here. I have to balance it out by dividing by 2 on the bottom. And so, really hiding out down here under square root of 3 is a 1. So that's all legal as long as I also divide that 1 by 2. And hopefully at that point we realize, oh yeah, I recognize that. When the y value, or the sine, is square root of 3 over 2 and the x is 1/2, that's when I'm right here on the unit circle. That happens when my angle theta is pi over 3. And so that's my answer to what the tangent inverse of the square root of 3 is. All right, so I just want to do a couple other little examples that involve the inverse trig functions. A couple of them are kind of applications of them. But first, example 9, let's just talk about doing this in your calculator. So we want to evaluate the inverse tangent of negative 1.3. The moment you see a value inside the argument of your inverse function that is not one of the special values, then we can just go ahead and pull out our calculator at that point. And so the thing to remember is that depending upon what mode your calculator is in, that will determine what kind of answer it spits out. So if you are in radians, then it's going to spit out an angle in radians. So the tan inverse of negative 1.3, by the way, this is just the second function of the tan button on your calculator. It's going to spit out negative 0.915. But that's in radians. And then if you go into mode and you switch your mode to degrees, then typing the same thing in, of course, gives you something completely different, because the tan inverse always spits out an angle. And if you tell it you want to be in degree mode, then it's going to give you an angle in degrees. I guess that's approximate. All right, so we can use our calculator to give us approximations of inverse trig functions. All right, this one asks us, okay, solve the triangle below for the angle theta. So we want to find this angle theta here. All right, so let's start this off not by jumping straight to inverse trig functions, but let's just look at what we're given in relation to this angle. Well, we're given the adjacent angle, I suppose, and the hypotenuse. So the moment I hear adjacent and hypotenuse, I should be thinking cosine. So this is the cosine of theta is equal to the adjacent 19 divided by the hypotenuse 24.8. But what I'd ask you to remember here is that remember originally when I was talking about inverse functions at the very beginning in the first slide, I used the example of trying to solve an exponential equation. And I took the natural logarithm of both sides because I made the comment that the natural logarithm undoes the exponential, and that's what inverses do. They undo the original function. So if I want to figure out what theta should be, let's just understand that this, right, is equivalent to saying theta equals the cosine inverse of 19 over 24.8. To view it more from the standpoint of kind of applying an operation to both sides of the equation, we could have thought of this as, let's take the cosine inverse of the cosine of theta. And that's okay as long as we also take the cosine inverse of 19 over 24.8. And of course the cosine inverse and cosine zap each other here essentially, so we get theta is equal to the cosine inverse of 19 over 24.8. Either way, you get the same thing, and so using our calculator to help us, the cosine inverse of 19 over 24.8 is approximately 40 degrees. So one last example here, that's an application problem. It says a ramp 20 feet in length rises to a loading platform that is 3 1/3 feet off the ground. What is the angle of elevation of the ramp? All right, so we got this, this ramp here. Gets to 3 1/3 feet off the ground, and I'm pretty confident that this drawing is not going to be to scale in any real way. But all right, there's my picture nonetheless. And it says the ramp itself is 20 feet in length, so that would be this part. Okay, so obviously, okay, 20 feet versus 3 1/3. I'm not sure I did a real good job of that, but close enough, I guess. And it's saying, what is the angle of elevation of the ramp? So that would be this angle right here. All right, but like in the last problem, we look at what we know. Looks like I know the opposite side, and I know the hypotenuse. So this time I should be thinking about the sine. So I know that the sine of theta is equal to 3 1/3 over 20. And really, okay, I know I'm dividing by 20, so this 3 1/3 really ought to be turned into an improper fraction. So the sine of theta is equal to 10/3 divided by 20. And I can do better than that. This could be 10/3 times the reciprocal of 20, so 1 over 20. And we get some nice cancellation there, I guess. So this all boils down to the sine of theta being equal to 1/6. But of course that then can turn into the fact that theta then would have to be the sine inverse of 1/6. In other words, what is the angle that if you took the sine of it, you got 1/6? And again, I can use my calculator to help me out here. So I get theta in this case is approximately, I think I have the wrong one. Let me calculate that real quick. So about 9.6 degrees.